An example of a discrete probability distribution that does not rely upon Bernoulli trials is the hypergeometric distribution. By definition, hypergeometric distribution applies to sampling without replacement. Bernoulli trials assume that you have sampling with replacement. Earlier in the class, you may have been exposed to this problem. We have a portable communications radio, uses 4 AA batteries. It can be powered successfully using either 4 fresh batteries or a combination of 3 fresh and 1 dead. We've got a collection of 22 batteries in our drawer. We know that there's a subset of 7 dead batteries. That means we have 15 fresh batteries. And we want to ask ourselves, what is the probability that a selection of 4 batteries from the drawer, when installed in the radio, will power the radio successfully? So first, let's consider the probability of obtaining in our first battery. So we're going to have 4 batteries over here. What is the probability of obtaining a fresh battery? On the first choice, we have 15 fresh. So that's going to be, we have 15 over 22. That's the probability of getting a fresh battery. And you can also see that the probability of getting a dead battery would be 7 over 22. So let's consider a couple different options. On the left, the first battery chosen is fresh, so we've already taken 1 fresh battery out. If we've removed 1 fresh battery from these 22 batteries, what's going to be the probability in the second choice, our second pick from the drawer, of getting a fresh battery? That's right, if we've already removed 1 battery in our first choice, there are 21 batteries remaining, but there will now only be 14 batteries that are fresh. So the second battery chosen, there's a 2/3 chance that it's going to be a fresh battery. Now, if we happened on the first battery to choose a dead battery, what is the probability that we're going to choose a fresh battery on the second pick? Similarly, we'll have 21 batteries remaining. If we chose a dead battery, then we'll still have 15 fresh batteries. And so the probability of getting a fresh battery on the second choice is 15 over 21. You can see that depending upon which battery is chosen first, we have a 2/3 chance on the left and a 15 over 21 chance on the right. So the probability of a success, defining a success as a fresh battery, changes depending upon what you choose. And so this is actually known as without replacement, trials without replacement. And we can't use Bernoulli trials. We can't use the binomial distribution, geometric distribution, nor negative binomial distribution. Instead, we're going to use something known as the hypergeometric distribution. In this analysis, we assume that the population is somewhat finite. We might have fewer than 100 items or so. And this is, again, sampling without replacement. There is a segment of the population that has a particular characteristic. Whether this is a defect or a success, the user kind of can define that, but this is known as capital K. We take a sample of size n, and that's denoted by this small circle down here. And in that small circle of size n, we're going to have an even smaller subset, x, that's going to correspond to the characteristic of interest. So little x has come from big K. The ways that we can take a sample of size little n from a much larger population, capital N, would be capital N, choose little n. It also turns out that the ways that a sample size of little x can be chosen from capital K is K, choose little x. And the total ways that the sample of n minus x can be withdrawn from capital N minus capital K is shown here. So combining all of this, the probability function for the hypergeometric distribution is as shown here, where the probability of getting exactly x number of successes in a limited sample size, where again capital N is less than about 100 or so, is given by this formula here. And this is known as the hypergeometric distribution. The mean is n times capital K divided by capital N, and the variance is given by this equation on the right, if you need to use those. So let's apply the hypergeometric distribution to this example that we looked at earlier. Here we're saying that we have a total of 22 batteries to choose from. We have 15, that's going to be our subset of interest. Those are fresh batteries. We take a sample size. We're saying our sample is the 4 batteries that go into the radio. That's size little n equals 4. And now we can recast our problem to be the probability of a successful radio would be the probability of getting exactly 3 fresh batteries plus the probability of getting 4. We need at least 3 batteries. This is also, by the way, because of how probability distributions work, they sum up to 100% or probability of 1. This is also 1 minus the cumulative probability function up to and including 2. And when we plug all of our numbers into the hypergeometric distribution formula and we do the math, we end up with about a 62.2% chance that we will get a successful radio. Now I wanted to go back and revisit this cumulative distribution, and I wanted to show you how we can do this in Excel. In Excel, there's a nice function to do this called the Hypergeometric Dist. Let's go ahead and do this. I've got K up here that I've named big K. I've named N here, actually big N, B-I-G-N, because you can't name little n and big N, the same variable. I've named little n up here in the name box, and I can just use the hypergeom.dist function. The sample S is the number of successes in our sample. So that's going to be, we want to use our independent variable there. So this is the probability that we'll have exactly 0 successes in our sample. The number in our sample is going to be little n. The population successes, that's capital K. The number in our population, that's big N. And I'm going to do false here for non-cumulative distribution. That means the probability of getting exactly 0 successes or 0 fresh batteries is very small. I can copy this down because of the way that I did this. I wanted to just note that you can't have 5 successes. X can never be greater than the sample size. So it just spits out a 0, but really that doesn't make any sense. So just make sure that X can only be less than or equal to the sample size. And so the probability of a successful radio would be the sum of F of 3 and F of 4, 0.622, which is what we got earlier by hand. I wanted to also revisit this 1 minus capital F of 2. We can do that in Excel by using a single formula. The sample successes is going to be, I'm doing 1 minus F of 2, so 2. The number in our sample is little n. The population successes is K. The number in our population is big N. And in this case, I'm going to use true because that'll be a cumulative. So it's going to sum 0, 1, and 2. It's going to subtract that from 1, and we can do that in one fell swoop. So the answer is 0.622. Thanks for watching.